We can describe the efficiency of an algorithm, a program, or a programmatic operation in terms of the time it takes to do its work, or the amount of memory it uses, or the amount of secondary storage space it needs. These can be useful things to know, but of course the performance of a program depends on the capabilities of the computer it's running on. A program that's sluggish on today's computers might be twice as fast on next year's model. Big O notation tells us something else. Big O describes the way that the time taken by a program depends on the amount of data it has to work with. Big O tells us how well a program scales. We say that Big O describes the complexity of a program. Common sense tells us that a program takes longer when it has more data to process. This is true in the case of a simple linear search. If the target value happens to be at the end of the list, then having to search through twice as much data would double the time taken. But this is not the case for all algorithms. In this video, I'm going to illustrate some Big O complexities with made-up data and charts. I'm also going to talk about some well-known algorithms and how their Big O complexities can be derived. These are the algorithms I'm going to be looking at. Let's start with the linear search. The linear search is sometimes referred to as a sequential search. An unordered list is searched for a particular value. Each and every value in the list is compared with the target value. This is something of a brute force approach. It's usually implemented with a simple loop. Looking at the pseudocode for a linear search, we can see that the loop visits and tests each item in turn. If the target value is found, a Boolean variable is set to true and there's a forced exit from the loop. This is what it looks like. We're searching this list for a target value of 63. Notice that the target value is at the end of the list. It takes a certain amount of time to find it. If we double the amount of data and our target value is still at the end of the list, you can see it's taking twice as long to find the target. Double the amount of data again and it takes twice as long again. In fact, if we triple the amount of data, it'll triple the time taken. There's a nice, simple relationship between the amount of data and the time taken by the linear search. This is what it looks like on a chart. There's a nice, simple relationship between the amount of data and the time taken to process it. The time taken is directly proportional to the amount of data. The gradient of the line, of course, depends on the computer that's running the program, but at the end of the day, it's still going to be a nice, straight line. In terms of Big O complexity then, for n items of data, the time taken is equal to some constant multiplied by n. The constant depends on the computer. The Big O time complexity is said to be linear. And in Big O notation we write O brackets n. This chart therefore describes all algorithms which follow linear time complexity. Now let's look at our next Big O complexity. We're going to look at operations of the stack data structure. With a stack, items are pushed onto and popped off the top of the stack. A stack might also include a peek operation, which looks at the top item without actually removing it. A stack is known as a last in, first out data structure. And it's usually implemented with an array and a pointer to the top item. Here's some pseudocode for a stack push operation. As long as we don't exceed the maximum size of the stack, then you can see the top pointer is being incremented and then the new item is placed in the appropriate position of the array. And this is our stack pop operation. An item is copied from the array position given by top, and then top is decremented. This is what it looks like. We have a stack with two items. Top is pointing to the second item. When we want to push a new item onto the stack, we increment top, and the item is copied into that position. To pop an item from the stack, it's copied from the position given by top, and then top is decremented. Notice that we don't necessarily remove the item from the stack. It'll be overwritten next time we push something else onto it. In terms of complexity, it takes a certain amount of time to push an item onto the top of the stack. If we double the amount of data, it takes exactly the same amount of time. Similarly, removing an item from the top of the stack takes a certain amount of time. Removing an item is independent of the amount of data in the stack. Plotting this information onto a chart, you can see we have a nice flat line. No matter how much data there is, the time taken stays the same. The units that we're using for the time are not relevant here. That could be 500 microseconds. It could be 500 minutes. It doesn't really matter. As far as big O complexity is concerned, what matters is that it's always the same. So in terms of complexity, increasing the amount of data makes no difference to the time taken by push or pop. The big O complexity is known as constant, and in big O notation we write O brackets 1. This chart therefore describes constant time complexity. Before we talk about the time complexity of our next algorithm, let's briefly review a mathematical principle, namely the concept of a dominant term in an expression. Suppose we have an algorithm which is working on a data structure of size n. We might find that it takes 5 times n to the power 3 plus n to the power 2 plus 4n plus 3 steps. As n gets bigger, the smaller terms become less and less significant. The term 5n to the power 3 grows so quickly that the other terms just don't matter. They get swallowed up. So we can ignore everything after 5n cubed. In fact, we can also ignore any constants. So the big O time complexity of this algorithm is O(n cubed). We call this cubic complexity. So now let's consider the bubble sort. This is probably the first sorting algorithm you ever learned about, because it's relatively simple to understand and easy to implement. The bubble sort is the stairway to heaven of sorting algorithms. The bubble sort sorts a list of items into numeric or alphabetical order. It scans a list, comparing pairs of values and swapping their positions if necessary. For n items of data, the list has to be scanned like this, n-1 times. There's all kinds of enhancements you can make to the bubble sort to improve its performance, but let's talk about the basic algorithm first. The pseudocode for a bubble sort involves a loop to scan the array, comparing pairs of items and swapping them if necessary. If there are 5 items to sort, that is, if n equals 5, then there's 4 pairs of items to be compared. So this loop only needs to run 4 times. Since the array is probably 0 based, this loop counts from 0 to n-2. There's no detail here about how the swap takes place, but this is usually implemented with a temporary variable. Then there's an outer loop to ensure that this scan runs n-1 times. This is what it looks like. We compare a pair of values and swap them if necessary. We have 5 values here, so we're going to scan through the list 4 times. Eventually, all of the data will be in order. Now let's double the amount of data it has to work with. And notice that if we want to sort these into ascending order, the data is in completely the wrong order. Just as before, pairs of values are compared and swapped if necessary. Notice that the larger values are making their way to the end of the list, rather like the ripples on the surface of a pond when you throw a pebble into it. That's why this is called a ripple sort. It's quite clear that even if we speed up this animation, it's taking more than twice as long with twice as much data. In fact, you can imagine if we double the amount of data again, it's going to take an awful lot longer. When we plot the amount of data versus the time on a chart, you can see that the curve is growing very, very quickly. Doubling the amount of data actually quadruples the time taken. If we triple the amount of data, we increase the time taken by a factor of 9. So describing this in terms of complexity, for n items of data, a simple implementation of the bubble sort takes n-1 multiplied by n-1 operations. If we expand these brackets out, it can be written n squared minus 2n plus 1, and you can see the dominant term is n squared. This is known as quadratic complexity, and in big O notation we write O and in brackets n squared. So this chart actually describes quadratic time complexity. We can enhance the bubble sort. You'll have noticed that after the first pass of the inner loop, the largest value finds itself in the correct place. After the second pass, the second largest value is in the correct place, and so on. Now this means that the inner loop can run one less time with each pass of the outer loop. In terms of pseudocode, we can make a very simple adjustment to the program to achieve this. So what's the impact on the complexity? Well, for n items of data, the enhanced bubble sort algorithm performs n-1 plus n-2 plus n-3 all the way down to 3, 2 and 1 operations. Now without going into the mathematics, this can be shown to be n squared minus n divided by 2. And this gives us a 50% reduction in the time taken. But the dominant term is still n squared. So even our enhanced bubble sort still has quadratic complexity. Remember, complexity is describing the way that the time taken grows according to the amount of data. There's another enhancement we can make as well. If the inner loop doesn't perform any swaps, then the data must now be in the correct order. So we can check for swaps with a Boolean variable, and we can force an exit from the bubble sort when there's no more work to do. This is what the pseudocode looks like. And this introduces another concept, that of best and worst case scenario. With our bubble sort, if the data is already in the right order, the inner loop will run only once. So in the best case scenario, the bubble sort actually has linear complexity. In the worst case scenario with the bubble sort, the data is in completely the wrong order, so everything has to be moved. In the worst case scenario, the bubble sort has quadratic complexity. With big O, it's normally the worst case scenario that we're interested in. Before looking at the next algorithm, let's take another brief diversion to understand another important concept of mathematics, that is, the concept of logarithms. Logarithms were discovered by a mathematician called John Napier in the 1500s. They've been used ever since by scientists and engineers to simplify calculations. Just as subtraction is the inverse of addition and division is the inverse of multiplication, logarithms are the inverse of exponentiation. For example, you probably already know that 2 to the power of 3 means 2 times 2 times 2, which is 8. We say that 2 is the base and 3 is the exponent. Therefore, the logarithm of 8 is the exponent, that is the power to which the base of 2 must be raised in order to give us 8. We say the base 2 log of 8 is equal to 3. In the same way, if 10 to the power of 4 is 10 times 10 times 10 times 10, namely 10,000, then the base 10 log of 10,000 is 4. In general terms, we can say that if x to the power of z is equal to y, then z equals the log in base x of y. Strictly speaking, the base can be in any number, but in computer science, and particularly when we're using big O, we generally work with base 2 logs. Let's take a quick look at some more base 2 logs. If 2 to the power 0 is 1, then log in base 2 of 1 is 0. If 2 to the power 1 is 2, then the log of 2 is 1. If 2 to the power 2 is 4, then the log of 4 is 2. 2 to the 3 is 8, then the log of 8 is 3. We've seen that one already. 2 to the power 4 is 16, therefore the log of 16 is 4. And if 2 to the power 5 is 32, then the log of 32 is 5. Notice that each number here that we're calculating the log of is twice as big as the previous number, but each log is only one bigger than the previous value. So what does that matter? Well, let's take a look at our next algorithm, the binary search. The binary search is used to search an ordered list for a particular value. The binary search takes a divide and conquer approach. The target is compared with the middle value, and then half of the list is discarded. And this happens repeatedly until the target value is found. This is very efficient for large, sorted lists. Here's some pseudocode. It starts by establishing pointers for the bottom and the top of the data array by assigning its lower and upper bounds to a pair of variables, I-low and I-high. These pointers define the section of the array that the program is looking at, all of it to begin with. Inside a loop, these pointers are used to calculate the middle position of the array and to check to see if it contains the target value. If not, then, depending on the value in the middle, it effectively discards half of the list by redefining one of the pointers. It might redefine I-high to discard the top half of the list, or I-low to discard the bottom half of the list. This is an iterative approach to implementing a binary search, but this algorithm also lends itself to a recursive implementation because we're repeatedly solving smaller and smaller versions of the same problem. Either way, the time complexity is the same. Let's see how it works. Let's suppose our target value is 63. We establish the middle and compare it with the target value. The target value is bigger than 58, so we discard the lower half of the list. And then we do it again. We discard the top half of the list this time. And then we do it again. And we discard half of the list again. In this case, we've arrived at the correct value. And we chopped the list in half 3 times to do this. That's why it's sometimes called a binary chop. Let's do it again, but this time with twice as much data. We check the middle value. We discard half of the list. We do it again and discard half of the list. And again, discarding half of the list. And eventually we get there with 4 chops. Let's take a look at this graphically. Look at the data first. Notice that each value in the data column is double the one before it. And notice that the time values are increasing by 1 unit each time. You can see that the line climbs quite steeply to begin with, but then it begins to level out. That tells us for very large amounts of data, the performance degradation isn't terribly significant. In terms of big O complexity then, doubling the amount of data requires only 1 extra chop. This makes the binary search very efficient for very large data sets, if the data is already sorted. The big O time complexity then is logarithmic. And we write O brackets log n. And what we're seeing here then is the classic chart for any algorithm which has logarithmic time complexity. There's one more algorithm I'd like to consider then, and that's the merge sort. The merge sort, of course, sorts the data in a list. It takes a divide and conquer approach. It does so by splitting a list into several sublists, each of which contains only 1 item and is therefore, by definition, sorted. Then, pairs of sublists are merged back together, sorting as it goes. This is how it works. We have a list which needs to be sorted. We split it into 2. We then split each sublist again. And then we split each sublist again. We now have 8 sublists. Each sublist contains only 1 item of data, so each sublist is sorted. Now we start to merge pairs of lists back together again, sorting as we go. And eventually we have a fully sorted list. Let's have a think about the merging process, which is the most expensive part of a merge sort. To turn 8 sublists each of 1 item into 4 sublists of 2 items, we had to perform 8 append operations. Then, to convert 4 lists each of 2 items into 2 lists of 4 items, we had to perform another 8 append operations. And then finally, we performed another 8 append operations. So we've performed a total of 8 times 3 append operations. So let's derive a big O time complexity from this. We've seen that if n equals 8, the merge sort does n times 3 append operations. We know that the log of 8 is 3, so the log of n is 3, and it follows that we did n multiplied by the log of n append operations. This generalisation is correct for other amounts of data too. If we had 16 items to sort in our list, a quick sketch would reveal that we'd need 16 times 4 appends. The log of 16 is 4, so n log n holds true. We haven't concerned ourselves with the splitting part of the merge sort process because, if you think about it, this has the same time complexity as the merge. It scales at the same rate, so its impact on the overall process is merely constant. Cast your mind back to our discussion about dominant terms. So the big O time complexity of the merge sort is a cross between linear and logarithmic. We can call this linearithmic. And in big O notation we write O brackets n log n. This is what it looks like on a chart. And any other algorithm with n log n complexity can be illustrated with a similar looking chart. Let's summarise then. With constant time complexity, no matter how big the data structure, the number of operations, and therefore the time taken, is fixed. Exactly what that time is depends of course on what the program is actually doing and the capabilities of the computer it's running on. The raw performance may be very good or it may be very poor. This is not what's relevant as far as big O is concerned. What matters is the time taken is independent of the amount of data that the program is given to work on. Constant time complexity is considered ideal. Examples include the push and pop and peek operations of a stack data structure, the NQ and DQ operations of a linear or a circular queue, and inserting a node into a linked list. With linear complexity, the time taken by a program is directly proportional to the amount of data it's given to work on. This is a nice straight line when plotted on a chart. Doubling the number of data items doubles the time taken. Tripling the amount of data triples the time taken, and so on. Linear complexity is considered good, but a program that scales according to linear complexity can be unacceptably slow with very large data structures. The linear search is an obvious example of an algorithm that exhibits linear complexity. Other examples include traversing a linked list, counting the items in a list, comparing a pair of strings. In fact, all kinds of algorithms that take a brute force approach to working with lists have probably got linear complexity. With quadratic complexity, the number of operations and therefore the time taken by a program is proportional to the square of the amount of data it starts with. Twice as much data takes 4 times as long to process. 3 times as much data takes 9 times as long to process. This is considered poor scalability. A program that scales with quadratic complexity can be unusably slow with large amounts of data. Examples include the bubble sort and the insertion sort, and traversing a 2-dimensional array. Polynomial complexity is a general term for any complexity in which the time taken is proportional to the amount of data raised to the power of some constant. We'll call that constant k. If k is 2, it's known more specifically as quadratic complexity. If k is 3, it's actually cubic complexity. K can in fact be any number. Linear complexity is also an example of polynomial complexity because in this case k is 1. Any number raised to the power of 1 is itself. N raised to the power of 1 is just n. Strictly speaking, constant complexity is also polynomial because any number raised to the power of 0 is 1. With constant complexity, k is 0. In the case of logarithmic complexity, the time taken is proportional to the base 2 logarithm of the number of items in the data structure. This means that if the amount of data doubles, the number of operations and therefore the time taken grows by only 1 unit. This is good scalability. Plotted onto a chart, we see a steep curve to begin with, but then it starts to level out. This means the impact of increasing the amount of data a program has to work with lessens when it's asked to work with very large data structures. Examples include performing a binary search on a pre-sorted list, or searching a binary tree. In fact, logarithmic complexity often typifies algorithms that take a divide and conquer approach. With linearithmic complexity, the time taken is proportional to the logarithm of the number of data items multiplied by the number of data items. This complexity is on a par with linear. The increase in time is reasonable for relatively small increases in the amount of data, but the impact on performance of very large data structures can be unacceptable. Examples of algorithms that display linearithmic complexity include the merge sort and the quick sort. Finally, with exponential complexity, the number of operations and therefore the time taken by a program grows in proportion to some constant raised to the power of the number of items in the data structure. This means that if the constant is 2, the program takes twice as long when asked to work with only 1 extra unit of data. If the constant is 10, then 1 extra item of data can slow it down 10 times. Needless to say, this is very poor scalability. An algorithm with exponential complexity can become intolerably slow almost immediately. That's not to say that programs that scale with exponential complexity are useless. If you're happy with the way a program performs when it's given a certain amount of data, then you'll probably be happy with its performance on another occasion when it's given the same amount of data again, or for that matter, when it's given less data. Scalability just might not be an issue for you. A classic example is a program to solve the n queens problem. For example, can you place 4 queens on a 4x4 chessboard so that no 2 can take each other? Now what about 8 queens on an 8x8 chessboard? Other examples include some implementations of the travelling salesman problem, or a password cracking program that operates by brute force. So remember, big O complexity is not about the raw performance of a program. It's about how well a program scales. It's about how well a program maintains its performance when given more data to work with.